Section 12.3 is double integrals and polar coordinates. It's a really useful tool or method to have in our back pocket for integrating certain regions in the plane. We'll see a little bit of polar coordinates as we've looked at them in the past and extend that into integrating functions over planar regions expressed by polar coordinates. So remember that points x, y in the plane can be converted to polar coordinates r theta. For a review on that, you can look back into chapter 7, I believe, or chapter 8, somewhere in the past for Calc 2, or a trig textbook could do the same. But here are essential conversions from x, y components into r theta components. All three of these are the most useful. Of course, there's one more involving tangent of theta is equal to y over x. That won't be as essential for this section, though it could be useful in more general settings. Now, in order to establish this theory of integrating over a polar region or integrating in polar coordinates, we need to think about a polar rectangle. So a polar rectangle is essentially what I've drawn below here. Now this is a rectangle that's bounded by two angles in some sense, and it's polar rectangle in that it's bounded here by two angles. And even though these are curves, this is essentially our quote-unquote polar rectangle. So those two curves are radial lines. That's a radius of A and radius of B for the inner and outer, respectively, A and B. And our overall rectangle we're calling R. And of course, if we're going to try to integrate a function, some three-dimensional function that exists, a surface that's above this region, in other words, we're going to try to integrate over this, or that function over this region, then we need to first think about subdividing that region into subrectangles Rij. So here's a smaller version with two radii, r sub I and r sub I minus 1. And we need to talk about the area in one of those subrectangles. So the area of this subrectangle is given by delta ij, corresponding to Rij, the ith radius and jth angle. So delta A, the area of this ith jth subpolar rectangle, is 1/2 r squared theta minus 1/2 the other radius squared theta. Now, this is the outer radius, this is the inner radius, so we're doing something like finding the area here and then subtracting the area within that sector. So subtracting the area of the smaller sector from the larger sector, and that gives us exactly the area inside this portion of a sector, this segment of a sector. Remember that the area of a circular sector is 1/2 r squared theta, and that's where each of these multiples are coming through, okay, are coming from. So we can factor this expression here into ri plus ri minus 1 times ri minus 1 as a difference of squares. In doing so, we get a nice formula here that as we shrink these subrectangles down to dimensions that are approaching 0, so the radii are getting smaller and smaller, the point that's within this rectangle it becomes sort of solidified as Rij star theta ij star, and becomes exactly the point r theta that we're interested in the limit eventually. But as we shrink them down, that means that these two values become the same in the limit. So we have 2r times 1/2. So we have a factor of r. This difference, which is delta r, is really, in the limit, it's going to be dr. So our formula ends up with a r dr d theta in it when we take the limit as the dimensions r ij star, or r I and theta j go to 0. In other words, our area goes to 0. So in the limit, that's why we have an extra factor of r in the integral formula we see in the next page. So this is our conversion from some given region in the plane, integrating f of x, y over that region. It's equal to alpha to beta, the angle measure, from angle alpha to angle beta, radius A to radius B. Our cosine theta is x, our sine theta is y, so those are our substitutions for our rectangular, into our rectangular coordinate function. And r comes from what we just discussed in the formula, taking the limit of the double Riemann sum of the previous page. dr was the difference in rij, or ri and ri minus 1, and d theta is, well, that was the delta theta, theta j minus 1. So this is our formula. So without really seeing the derivation, one could just memorize this formula as well. It's nice to see why this r shows up, because it makes the formula easier to remember. But if not, just memorize the formula directly. So to use it, evaluate the double integral over r, where r is the region in the first quadrant enclosed by the circle x squared plus y squared equals 4, and the lines x equals 0 and y equals x. So we're given everything in rectangular coordinates. What we realize, though, is that they're asking for a sector of a circle. They're saying we have this circle, x squared plus y squared equals 4. We want to find the area of this function given in the integrand, or the volume enclosed underneath this function given in the integrand, or at least evaluate the double integral. If that function is not always positive, it won't necessarily be volume. But at any rate, in this given region right here. So over that region, we want to find the double integral of this function. Now, we could set this up as a rectangular integral. That would be just fine. It might be very difficult to deal with. In fact, when we start to deal with x squared plus y squared equals 4, a circle like this, setting up a double integral in this means we're going to have to solve for one variable. We're going to have square roots of difference of squares, things like that, and it could get a little bit complicated. So whenever we see a region that involves something circular or circular sector or circular surfaces intersecting one another, it's a good idea to consider polar coordinates, because that could simplify the work. Or in other words, if we see quadratic terms, x squareds, y squareds, things like that showing up, it might be worthwhile to consider polar coordinates. Okay, so in this case, it's exactly what we do, since that's the exercise anyway. We convert our function f of x, y equals 2x minus y to a function of r and theta. That's that direct substitution of r cosine theta, r sine theta. So we end up with this. Our old 2x minus y becomes that highlighted expression now. And having a look at the picture, we realize that our angles, x equals 0 is the angle theta equals 0. Y equals x has angle pi over 4. If we needed to, we could use arctangent to sort that out for x equals 0 and y equals x. We could pick a point on the line y equals x. 1 comma 1 is ideal. Take the arctangent of y over x. 1 over 1, arctangent of 1 is pi over 4. That would be the way to go about that. So in other words, pick a point on there. If we absolutely needed this, I don't think it's necessary, but the arctangent of y over x, any point on our line, is equal to theta. Okay, we could use that in between if we were a little bit lost with a given point or a given line that was given to us. Okay, in order to find that for 0, we'd have to realize that, well, arctangent is not defined there. Well, that must mean that theta is either 0 or pi. In this case, x equals 0. They're telling we see the wedge that's formed by this circular region. So continuing from here, we've got our angles. So now we would work on the radius. Well, this circle has radius 2, since r squared is 4. So we're going to integrate from 0 to 2, radius of 0 to radius of 4, from the pole outward to a radius of 2, of the function f of x, y, which is now converted to r theta, times r, part of the formula, dr d theta. Okay, now combine like terms. R squared is out front here. We're integrating with respect to r, so it's a fairly straightforward integration or antiderivative. 1/3 r cubed from 0 to 2. So that leaves us with 8 over 3 minus 0 over 3. So it's 8/3. We factor that out to the front of the integral just to clean up our integrand. And now we're integrating with respect to theta, the function 2 cosine theta minus sine theta. That's a straightforward trigonometric integral. We evaluate from 0 to pi over 4, the limits of integration here. The rest of these are typical details, and we have 4 root 2 minus 8 over 3. I've called this V, volume. Again, that's just pretty typical to do so. Of course, this function would have to be positive over that entire region for this to absolutely be a volume. We didn't check that. Maybe it is, maybe it's not. But at any rate, it is the integral of that function over the region. Okay, so further work. If we have a given result here, if f is continuous on a polar region of the form theta is between alpha and beta, and then r is now a function of theta, we can integrate very similar to what we did in type 1 and type 2 regions from section 12.2. Now we just have a function of theta for the limits of r. So some problems will be given to us in this format. Now, whether or not we use that every time is up to us. So in the example given below, we're asked to find the volume of the solid below the paraboloid z equals 18 minus 2x squared minus 2y squared and above the xy plane. So we know from projections, or rather traces of this paraboloid, so setting y equal to 0, x equal to 0, that this is a paraboloid which opens downward thanks to the negatives in front of 2x squared and 2y squared. So here we've drawn it somewhat accordingly. We don't really need to sketch it if we know that it's opening downward. One thing that we'll want to know is when this paraboloid intersects the xy plane. We do that by setting z equal to 0 here. In other words, the intersection of the plane and this paraboloid is z equals 0, so 0 equals 18 minus 2x squared minus 2y squared, and we establish that that's the circle x squared plus y squared equals 9. So it's a circle centered at the origin with radius 3. Okay, so we were able to put all this together because that's the circle that this paraboloid intersects the xy plane at. Now, that's our region of integration down in the plane here. We are interested in everything above this circle that's contained within this paraboloid. So we describe that region as x squared plus y squared equals 9. That should actually be less than or equal to 9. Less than or equal to 9 to be fully accurate there. So that's good that we've gotten that. And if that's the case, to describe this circle in terms of an angle, it's 0 to 2 pi in r theta, and r ranges from 0 to 3. So that completely characterizes this circle x squared plus y squared less than or equal to 9, or this disk. It's a filled in disk here. And we'll label that real quickly as this is d, the disk in the plane here. Okay, so the integral over d of f of xy dA per infinitesimal area is from 0 to 2 pi, so that's our angle, 0 to 2 pi. Now our function r of theta is, well, it's just a constant function of theta. It's the same. We're going to go from 0 to 3 in along these radial lines. So it's it's a very special case of this general h1 of theta, h2 of theta. We input our function 18 minus 2 r squared cosine squared theta is x squared, and then minus 2 sine squared theta, r squared theta sine squared theta, that's the negative 2y squared that we had previously. We see r from the integral formula here, and then dr d theta, of course. So we integrate, well, first collect terms to simplify some things. We've factored out negative 2r squared from the negative 2x squared minus 2y squared to get cosine squared theta plus sine squared theta. This is just equal to 1, so that simplifies nicely. And we've got r times all of this expression. So we end up with 18r minus 2r cubed. Integrate with respect to r. Leaves us with 9r squared minus 1/2 r to the 4th. Evaluated from 0 to 3. and that's going to give us 81 minus 81 over 2 d theta. We integrate with respect to theta, and we get theta, and that's from 0 to 2 pi. So it's 2 pi minus 0 to all times 81 over 2, and that leaves us with 81 pi. This, in fact, is a volume because we've more or less visually confirmed that this surface is above the xy plane. It's positive everywhere within this region, so it is, in fact, a volume. Okay, so again, this wasn't much different from the first one. There's a little bit more work to do, but the radius that we find down here, or the radial values, can be functions of theta, and that works because our second integral is with respect to theta. Our outer integral is with respect to theta. So if we need to express r in terms of theta, that's always available to us. Sometimes that'll just be a constant function of theta. Okay, evaluate the iterated integral by converting to polar coordinates. So if we're given an integral, and it looks suspiciously quadratic, like it involves a circle or a semicircle or a quarter of a circle, this looks much like a semicircle in terms of the x-axis. And when we're given these components, it looks like it's isolating us to a quarter circle. Okay, so we rewrite the iterated integral as a general integral over a planar region, R, where R is described by these limits of integration, which we'll put together in the picture below. So having a look at that. So x ranges from negative square root a squared minus y squared, which would actually be all of this semicircle here. And y ranges from 0 to a. So we eliminate the bottom portion of this semicircle due to that constraint on the y-axis. So our region R is this. If we give it a little sketch like this, we can see what we need to do to convert this set R from rectangular coordinates to polar coordinates. We realize that we need to travel from pi over 2 to pi in theta, and well, our radius is going to range from 0 to a. And so now we've succinctly described our region as a polar region, in polar coordinates at least, and we can rewrite our function, which is f of xy equals x squared y. We rewrite that as r squared cosine squared theta for x squared and r sine theta for y. Now we can insert all of this into our polar integral formula. We'll integrate from pi over 2 to pi in theta, matching this, from 0 to a and r. And our function is as we've calculated here. We've got r squared cosine squared theta, r sine theta is r cubed cosine squared theta sine theta times r from the polar integral formula, dr d theta. Now, r times r cubed is r to the fourth. Integrate that to get 1/5 r to the fifth. We evaluate that from 0 to a. 0 to a. So these things look complicated, by the way, but this is only an integral with respect to r first. So it is nice and simple. It's just a power rule integral. Remember, functions of theta are constant with respect to r at this point. So this is 0 to a, and we end up with a to the fifth. That's a constant, so we'll factor that out to the front in a moment. And we're integrating with respect to theta now, this integrand. So that, with a change of, this is a prime candidate for u substitution. U is equal to cosine theta. Maybe down here we see that. U is cosine theta, so du is negative sine theta d theta. We want to change our limits of integration. That's done off to the side here. So all these details are handled. We have a factor of a negative show up, and we substitute everything in as we would for a normal u substitution. And the result of that is negative a to the fifth over 5, 0 to negative 1 now, changing our limits of integration, u squared du. So again, we just have a power rule antiderivative, and that leaves us with negative a to the fifth over 5, 1/3 u cubed from 0 to negative 1. And plugging this in, 1/3 times negative a to the fifth over 5 is this term out front, and we have minus 1 minus 0, plugging negative 1 minus the evaluation at 0 in to that function u cubed. And the result of that is a to the fifth over 15. Now this one's been called v. That's just out of habit. Is it actually positive? Well, yes, it is. If you look, x squared in this region is going to be positive since it's squared no matter what. It'll be positive. Y is going from 0 to a. It's also, we can look, realize it's in the upper half plane, so it's positive as well. So it's accurate to call that a volume too. We could just use the term v more abstractly and say, okay, we just think about this as some, they were just giving it the name v, but in fact, this one does represent a volume as well. Okay, so those are some of the basic polar coordinate integrals. One of the trickiest things typically is to interpret these regions as polar coordinates, polar regions. From there, the conversion of the functions is usually very straightforward. X is r cosine theta, y is r sine theta, so that should fall out nicely each time. A lot of times we'll have identities. We might see an integram which looks nicely like this. If we had something like over the region r, x squared, root x squared plus y squared dA, we might immediately realize this would be very nice to express as a polar integral because it simplifies that integram to just r. It's going to be very easy to express. We would just have to express capital R, the region, in terms of polar coordinates. So it's a very convenient tool for certain problems. And I think we've seen at least a couple of those in which it was so.